This is a traveling wave. Now we have a second wave, the blue one, that is traveling in the same medium along with the red wave. These two waves, the blue and the red one, they are coherent waves, which means they have the same wavelength and the same frequency. Now for these traveling waves, in this case, right now they are in phase, and now they're gonna be out of phase. They're gonna be in phase again and out of phase again. So for a particular time, we can determine the phase difference between both waves. So for example, in this case, when both waves are overlapping on each other, so the phase difference is 0. So if I move this way, the phase difference now will be 180 degrees, because here is 180 degrees. And if I move a little bit more, now the phase difference will be 360 degrees. So one is ahead of the other one. So that's the phase difference. In terms of the path difference, is determined by actually the length or distance of a wavelength. So in this case, one complete wavelength is one wavelength. This will be half, right? So in this case, the path difference is 0, and then here the path difference will be half of a wavelength, and the path difference here will be one complete wavelength. So one complete wavelength, they are separate from each other. That is the path difference. The phase difference in this case will be 360 degrees. The phase difference right here will be 90 degrees. Or as path difference, half of a wavelength. One is ahead of each other. Now, if the path difference between the blue wave and the red wave is 0, there is no difference in between both of them. So when we add both waves, we have the maximum constructive interference here. So it will be double this amplitude and double this negative amplitude. Likewise here. So we have constructive interference when the path difference between both waves is 0. When the path difference now is half of a wavelength, so you see one wavelength here is behind of the other one, so the path difference here is half of a wavelength. So now we have destructive interference. So when we add this positive vertical displacement with the negative vertical displacement, because they are coherent waves, they are the same. So what is going to happen is that we have complete destructive interference. So it will be like a flat line here, a flat line here, and a flat line here, so on. So for this screen, the bright fringes corresponds to the constructive interference between both waves that is coming from both slits. And the D for dark, that's when destructive interference occurs. So that will be destructive interference, and this will be constructive interference. So let's call the difference of the wavelength path difference. So right on this central bright fringe is when both waves, they are aligned like this. So the path difference between both is 0. For the next dark fringe, what's going to happen is these two waves, they are going to be in this position now, which means that they are going to be separate from each other with a path difference of half of a wavelength. So following the sequence, so the first one, the path difference is 0 right here. There is no difference between the blue and the red waves. Now I'm going to move for the next one. Now the path difference will be half of a wavelength. Now I'm going to move to the next one. Now the path difference between them will be one complete wavelength. Now I'm moving one more time. Now we are going to have here again destructive interference. So now the difference between them is 1 wave and a half, or 3/2 wave. Now following the sequence, I'm going to move half of a wavelength to the right. Now the path difference between both waves is 1, 2 wavelengths. Now with this explanation in mind, let's read what the problem is asking. Now let me read for you the description of this diagram. The wavelength of the light is 610 nanometer. The distance between the double slit and the screen is 2.7 meter. An interference pattern of bright fringes and dark fringes is observed on the screen. The centers of the bright fringes are labeled B and the dark fringes are labeled D. Point P is the center of a particular dark fringe, and point Q is the center of a particular bright fringe. The distance across 5 bright fringes is 22 millimeter. So before answering this question, I'm going to move forward to solve this one here, and then you go back to the prior question. So this question asks to state the phase difference between the waves meeting at Q. So it's asking here the phase difference, and we have talked about the path difference. So the phase difference is represented by the change in the angle between both waves. At Q, the path difference between both waves is 1 complete wavelength. That corresponds to 360 degrees. Because this is 0, this is 180 degrees, and this is 360 degrees. So that's the path difference between the blue and the red wave. Now the next question is asking the path difference in nanometer of the waves meeting at P. So path difference is represented by this. So remember, the path difference was determined by moving upward every half of a wavelength. So in this case, at the bright fringe, the center bright fringe, the path difference is 0. So both waves, they are completely in phase. Then the next one, for the dark one, we move half of a wavelength. For Q, we move one more, and now we have a complete wavelength. For P, which is the question that we are working right now, we are going to move one more time, and then the difference between both waves will be 1.5 wavelength. So at point P, 1 plus half of a wavelength is 3/2 of a wavelength. So the wavelength of this light was given this problem, which is 610 nanometer. So doing the substitution, so the answer, this is in nanometer, and the problem is asking nanometer. So when you solve this, you'll be 915 nanometer. So now let's go back to this question to state what meant by coherent. So here it states that the light waves leaving the two slits are coherent. So what happened here is that the light is going to pass through those two openings. And this light is going to split into two identical waves, like this. So those two waves, they are going to travel in the same medium, and they are going to interact with each other. So that's why the result of this interaction is going to create bright and dark spots that we call fringes. So when those two waves, they arrive together, so they produce a really bright fringe, a bright spot. And when they arrive one ahead of each other, they are going, because they are separate, they have a path difference. Now they are going to create a bright fringe, but not as bright as this one, which the path difference was 0. So because now they are one ahead of each other, and as they go, like they are ahead of each other, half of wavelength, one complete wavelength, 3.5 of wavelength, 2 wavelengths, and so on. So they are going to create bright fringes, but not as bright as the central one, because they arrive together. So those two waves, they are produced by just a single wave. After they pass through those two slits, they are identical waves. They have the same wavelength and the same frequency, and also the same phase difference. So to answer this question, coherent means the two waves, they have the same phase difference, or you can state the two waves, they have the same wavelength and frequency. Now moving forward, the next question is asking to determine the distance A between the two slits. So we are using the formula for double slit. The wavelength is equal to the separation between both slits times the separation between two consecutive bright fringes or dark fringes, and D is the distance between both screens. So rearranging this formula in terms of A is equal to the wavelength times the distance divided by the distance between fringes. Okay, so we have the wavelength, we have the distance, but we don't have the distance between fringes. We need to calculate this one. So this problem did not provide the distance between two bright fringes or two dark fringes. It gives the distance between this bright to bright, which is 22 millimeters. So let's count how many we have here. We have 1, we have 2, we have 3, we have 4. So 4 times x is equal 22 millimeters. So x is 5.5 millimeters. So because the answer is in meter, so we convert everything to meter. So that was nanometer and this was millimeter. So that we are using the corresponded 10 to the power for the prefixes nano and milli. So the separation between both slits is 3 times 10 to the minus 4 meter. So the next question is saying that a higher frequency of visible light is now used. State and explain the change to the separation of the fringes. So let's go back to the original formula for the double slit. Since A, which is the separation between slits, and the distance between both screens did not change, so let's ignore this fraction right here and look just the wavelength and the separation between fringes, because this is what they want to know. Now, with a higher frequency, what is going to happen to the wavelength? So frequency and wavelength of a wave, they are inversely proportional. which means that for a higher frequency, the wavelength is going to decrease. With the decrease of the wavelength, so the fringe is going also decrease. In practical ways, what this is going to happen is, since the fringe, which is the separation between two bright areas and two dark areas, so that they're gonna be closer to each other here than the original projection on this screen. So the separation between bright and bright is going to be closer, or dark and dark is going to be closer. Next question. The intensity of the light incident on the double slit is now increased without altering its frequency. Compare the appearance of the fringes after this change with their appearance before this change. Let me answer this question based on this information. The intensity of light is equal to the amplitude of a wave square, which means that if the light intensity increased, so means that the amplitude has increased. So this question is asking how will be the appearance of the fringes. So how you affect the bright and dark fringes on this screen. So bright fringes appear brighter because now it's taller, and dark fringes will be unchanged because it's already dark. The question also asks about the change in the fringes. Now, x is the distance between two consecutive bright fringes or two consecutive dark fringes, and depends on the wavelength, which didn't change because the frequency is the same. We say here without changing the frequency. So the wavelength is the same. The distance between both screens is the same. And A is the distance between the slits, which did not change at all. So X, which is the fringe separation, remain the same. So the fringe separation is unchanged. Now going back to the first question of this problem, state the principle of superposition. When two waves overlap, the resultant displacement is the sum of individual displacement of each wave. So in summary, this problem is related to double slit and the path difference between two waves that is going to leave this opening. They are going to interact with each other, and we are able to determine the path difference between those two waves that will produce bright and dark spots on the screen, and also change a couple things, like for example the frequency of this wavelength get higher. So what will be the result here on this screen? So we could conclude that the separation between those fringes, they are going to be smaller. And the last question is related to increase the intensity of the light and how is going to be changed here. So of course the bright fringes will be brighter, the dark will not have any change because it's already dark, and the fringe separation will remain the same.